The first Tyrannosaurus rex wouldn't walk the Earth for another 66 million years. Pterosaurs hadn't yet claimed the skies. The Mesozoic Era, the age of dinosaurs, was still an unimaginable stretch of deep time away. But the planet was far from empty. Across vast floodplains and under blood-red skies, monsters already ruled. Saber-toothed predators, the size of bears, stalked their prey with forward-facing eyes and blade-like fangs. Armoured herbivores, with parrot beaks, stripped vegetation from ancient plants. Bizarre tusked creatures dug burrows in sun-baked earth, while in murky rivers lurked amphibians with boomerang-shaped heads and jaws lined with needle-sharp teeth. This was the Permian period, the final chapter of the Paleozoic era, a span of roughly 299 to 252 million years ago. Life on land had exploded into forms never seen before or since. The supercontinent Pangaea stretched across the globe, creating climates so extreme that survival itself became an evolutionary arms race. Ruling over this savage, unforgiving world were the synapsids, proto-mammals that had conquered terrestrial ecosystems millions of years before true mammals even existed. They were the apex predators, the dominant herbivores, the ecological engineers of their time. Then, in a geological instant, it all ended. The Permian Triassic extinction, the most catastrophic mass extinction in Earth's history, obliterated roughly 90% of all marine species and 70% of terrestrial vertebrates. The monsters that had ruled for tens of millions of years vanished, making room for the dinosaurs that would inherit a devastated world. This is the story of those forgotten rulers, the Permian monsters that dominated Earth before the age of dinosaurs ever began. The world of Pangaea. The Permian Earth looked nothing like the planet we know today. All the major landmasses had collided into a single, massive supercontinent called Pangaea, literally meaning all Earth. This colossal landmass stretched from pole to pole, surrounded by a single global ocean called Panthalassa. The formation of Pangaea fundamentally altered Earth's climate systems, ocean currents, and atmospheric circulation patterns, creating environmental conditions unlike anything in modern times. The interior of Pangaea was a scorching desert wasteland. With no nearby ocean to moderate temperatures or provide moisture, the continental interior became one of the most extreme environments in Earth's history. Summer temperatures soared to deadly levels, while winters could be surprisingly cold. Rainfall was rare and unpredictable, concentrated in brief, violent monsoon seasons that alternated with months of brutal drought. Massive sand dunes stretched for thousands of kilometres, broken only by occasional oases, where life could gain a precarious foothold. The coastal regions told a different story. Along Pangaea's edges, where ocean moisture could still reach land, lush floodplains and river deltas supported rich ecosystems. These regions experienced seasonal flooding that brought nutrients and water, followed by dry seasons that tested every organism's ability to survive. The vegetation was dominated by seed ferns, conifers, ginkgos, and cycads, plants that had evolved strategies to endure the harsh, seasonal climate. Gone were the vast coal swamps of the Carboniferous, replaced by more drought-resistant plant communities adapted to aridity. Atmospheric oxygen levels during the Permian were lower than they had been in the Carboniferous, but still slightly higher than modern levels. Carbon dioxide concentrations fluctuated significantly throughout the period, contributing to periods of global warming and cooling. These atmospheric changes influenced everything from plant growth to animal respiration, shaping the evolution of Permian life in profound ways. The oceans surrounding Pangaea harboured their own strange inhabitants, massive reef systems built by sponges, corals, and other organisms fringed the coastlines. These reefs were biodiversity hotspots, teeming with bizarre marine life. Primitive sharks, armoured fish, nautiloid cephalopods with coiled shells, and the last remnants of trilobites clinging to existence. But even the oceans were changing as shifting currents and occasional anoxic events created dead zones where nothing could survive. This was the world the Permian monsters inherited, a world of extremes where only the most adaptable, the most innovative, and the most resilient creatures could thrive. The coenopsids that came to dominate this landscape weren't dinosaurs, weren't modern mammals, but something entirely different. They were evolutionary experiments, testing body plans and survival strategies that would eventually lead to mammals. But they themselves were unique creations of their time. They were the product of millions of years of evolution following the Carboniferous, when early tetrapods first mastered life on land and began their terrestrial conquest. The stage was set for one of the most dramatic chapters in life's history, a chapter written not by dinosaurs, but by creatures whose very names evoke alien worlds: Gorgonopsians, Dinocephalians, Pareiasaurs, Dicynodons. These were Earth's true first monsters, and their reign would be spectacular, brutal, savage, utterly unprecedented, and ultimately doomed. Dimetrodon, the sailback terror. Nothing captures the strangeness of the Permian world quite like Dimetrodon, a massive predator with a towering sail of skin stretched across elongated spinal bones, prowling the floodplains of what would become North America. Despite appearing in countless dinosaur books and toy collections, Dimetrodon wasn't a dinosaur at all. It wasn't even a reptile. Dimetrodon was a coenopside, a member of the lineage that would eventually give rise to mammals, including humans. It lived during the early Permian, roughly 295 to 272 million years ago, and it was the apex predator of its ecosystem. Dimetrodon was built like a killing machine. The largest species, Dimetrodon grandis, reached lengths of over 4 meters and weighed around 250 kilograms, roughly the size of a modern American alligator. Its skull was long and deep, packed with differentiated teeth that showed clear specialization. The front teeth were sharp and pointed for gripping, while the back teeth were blade-like and serrated for slicing through flesh. This dental variety, heterodonty, was revolutionary for its time and represented an early step toward the complex tooth patterns seen in mammals. The jaws of Dimetrodon were powered by massive temporal muscles that attached to the sides of its skull. These muscles gave it a devastating bite force, capable of puncturing the thick skin and even the bony armor of its prey. Bite marks found on fossil bones show that Dimetrodon targeted other large synapsids, including early herbivores like Edaphosaurus and Diadectes. Some fossils even show evidence of intraspecific combat, Dimetrodon fighting other Dimetrodon, possibly over territory or mates. But the most distinctive feature of Dimetrodon was undoubtedly its sail, a massive, fan-like structure rising from its back. This sail was formed by extremely elongated neural spines, extensions of the vertebrae that could reach over a meter in height. A thin membrane of skin, rich with blood vessels, stretched between these spines. For over a century, paleontologists have debated the function of this extraordinary structure. The leading hypothesis suggests the sail was a thermoregulatory device. By orienting its body perpendicular to the sun, Dimetrodon could heat its blood quickly in the morning, warming up faster than prey or competitors. Conversely, by positioning the sail parallel to the wind or in shade, it could cool down during the hottest parts of the day. Computer models and biomechanical studies support this idea, showing that the sail could significantly affect body temperature. This gave Dimetrodon a critical advantage in the temperature extremes of Permian floodplains. Alternative theories propose that the sail served as a display structure for attracting mates or intimidating rivals. The sails show individual variation in size and shape, which would support a role in sexual selection. Some specimens show evidence of sexual dimorphism, with males possibly having larger or more elaborate sails than females. It's entirely possible the sail served multiple functions: thermoregulation, display, and species recognition all at once. Dimetrodon inhabited river valleys and floodplain environments where water was at least seasonally available. Fossil assemblages show it lived alongside a diverse cast of other early synapsids, amphibians, and early reptiles. The ecosystem was transitioning from the swamp-dominated Carboniferous to the drier conditions that would characterize the later Permian. Dimetrodon was perfectly adapted to this transitional world, combining reptilian efficiency with early mammalian innovations. Its hunting strategy likely combined ambush tactics with short pursuit bursts. Dimetrodon wasn't built for marathon chases. Its limbs were relatively short and splayed outward from its body, limiting its speed and endurance. But in short bursts, it could strike with devastating effect, using its powerful jaws and serrated teeth to deliver crippling wounds. Prey that escaped the initial attack often succumbed to blood loss or infection. Dimetrodon's success is evident in its fossil abundance and species diversity. At least a dozen species have been identified, ranging from small, metre-long juveniles to the massive D. grandis. This diversity suggests Dimetrodon occupied multiple ecological niches, with different species specializing in different prey sizes and hunting strategies. For millions of years, Dimetrodon reigned as the top predator in its environment, a position of dominance rarely achieved in evolutionary history. But even apex predators are subject to the whims of evolution and environmental change. By the Middle Permian, Dimetrodon had vanished, replaced by more advanced synapside predators. The exact cause of its extinction remains unclear, but climate change and competition from new predator groups likely played roles. The world was changing, and even the mighty sailback terror couldn't adapt fast enough. Still, its legacy lived on in the evolutionary innovations it pioneered, innovations that would eventually lead to the mammals that rule Earth today. Edaphosaurus, the herbivorous rival. While Dimetrodon terrorized the early Permian as an apex predator, another sailback synapsiid thrived in the same ecosystems, but with a completely different survival strategy. Edaphosaurus was a herbivore, one of the first large vertebrates to successfully specialize in eating plants on land. Living roughly 303 to 265 million years ago, spanning the late Carboniferous into the early Permian, Edaphosaurus represented a revolutionary shift in terrestrial ecosystems. Before its appearance, most large land vertebrates were carnivores or insectivores. Edaphosaurus pioneered a lifestyle that would eventually support the massive herbivore diversity seen in later periods. Edaphosaurus was built like a living tank. It could reach lengths of over 3 meters and weigh more than 300 kilograms, making it one of the largest animals of its time. Its body was barrel-shaped and robust, with a wide rib cage that housed an enlarged digestive system. This expanded gut space was essential for processing tough plant material, which requires longer digestion times and often bacterial fermentation to break down cellulose. The broad body also provided stability, allowing Edaphosaurus to reach upward to browse on vegetation that smaller animals couldn't access. Like Dimetrodon, Edaphosaurus possessed a dramatic sail rising from its back, but with one crucial difference. Its sail was covered in distinctive crossbars or tubercles that protruded horizontally from the neural spines. These bumpy projections gave the sail a unique, almost bristly appearance, unlike any other sailback synapside. The function of these crossbars remains mysterious. They may have provided attachment points for additional blood vessels, enhancing thermoregulation. They might have served as structural reinforcements, preventing the tall spines from breaking. Or they could have been display structures, making the sail even more visually striking during social interactions. The skull of Edaphosaurus was small relative to its body, but highly specialized. Unlike the long, deep skull of Dimetrodon, with its differentiated predatory teeth, Edaphosaurus had a short, blunt head with peg-like teeth arranged in dense clusters. These teeth weren't designed for cutting or tearing flesh, they were grinding tools. The jaws also featured additional tooth plates on the palate and inner surfaces of the lower jaw, creating a complex grinding mill perfect for crushing plant material. This dental arrangement was remarkably sophisticated for its time and represented one of the earliest examples of specialized herbivore dentition in vertebrate evolution. Feeding behavior in Edaphosaurus likely involved cropping vegetation with its front teeth, then using the internal tooth plates to crush and grind the material into a digestible pulp. The jaw mechanics show limited side-to-side motion, suggesting a primarily vertical crushing action rather than the complex chewing seen in later herbivores. Still, this was a massive improvement over simply swallowing plant material whole, as many earlier herbivores had done. By mechanically processing food in the mouth, Edaphosaurus could extract more nutrients and handle tougher plant species. The ecosystem role of Edaphosaurus was transformative. By converting plant biomass into animal tissue, it created a new food source for carnivores and opened up energy pathways that hadn't existed before. Herbivores like Edaphosaurus became the foundation of terrestrial food webs, supporting populations of predators like Dimetrodon, while simultaneously shaping plant communities through their feeding activities. Areas where Edaphosaurus was abundant would have looked different from areas where it was absent, as its browsing pressure selected for plants with different growth strategies and defensive adaptations. Fossil evidence suggests Edaphosaurus preferred lowland environments near water sources, where plant diversity and density were highest. Bone beds containing multiple Edaphosaurus individuals hint at possible social behavior, or at least aggregation at favored feeding sites. Whether they actively traveled in herds or simply converged on resource-rich areas remains debated, but their abundance in certain fossil localities indicates they were successful animals that thrived in appropriate habitats. The relationship between Edaphosaurus and Dimetrodon, herbivore and carnivore, both sporting similar sails, has fascinated paleontologists for decades. They coexisted for millions of years in the same environments, creating a predator-prey dynamic not unlike modern African savannas, where lions hunt zebras and wildebeest. The convergent evolution of their sails, despite their vastly different lifestyles, suggests that thermoregulation was indeed a critical challenge in Permian ecosystems, one that both predators and prey needed to solve. By the Middle Permian, Edaphosaurus disappeared from the fossil record, outlasted slightly by its predatory counterpart Dimetrodon, but ultimately succumbing to the same forces of environmental change and evolutionary turnover. More advanced herbivorous synapsids were evolving, with better locomotion, more efficient digestive systems, and improved defensive adaptations. Edaphosaurus, for all its innovations, was an early experiment, successful for millions of years, but ultimately replaced by creatures that refined the herbivore lifestyle even further. Its legacy, however, endures in every mammalian herbivore alive today, descendants of the lineage it helped pioneer. Dinocephalians, the terrible-headed giants. The Middle Permian witnessed the rise of creatures so bizarre and massive that their very name means terrible heads, the Dinocephalians. These were synapsids that pushed body size to extremes never before seen in terrestrial vertebrates, with some species reaching lengths of 5 meters and weights exceeding a ton. They dominated ecosystems across Pangaea, particularly in what is now Russia and South Africa, from roughly 272 to 260 million years ago. Dinocephalians represented peak synapside diversity and ecological dominance, but their reign was spectacular and brief, ending in a mysterious extinction event that cleared the stage for their successors. Dinocephalians split into two major ecological groups, herbivores and carnivores. each pushing evolutionary boundaries in different directions. The herbivorous Dinocephalians, like Moschops and Dinocephalus, were massive animals built like living battering rams. Moschops could reach 4 meters in length, with a barrel-shaped body supported by pillar-like legs, positioned more upright than earlier synapsids. This improved posture allowed them to support tremendous weight while moving more efficiently than their sprawling predecessors. The skull of Moschops was extraordinarily thick, particularly on top of the head, where the bone could exceed 10 centimeters in thickness. This thickening wasn't for protection from predators. It was for combat with rivals. The wear patterns and bone structure strongly suggest that Moschops engaged in head-butting behavior similar to modern bighorn sheep or musk oxen. Males likely crashed their skulls together in dominance displays, competing for territory or access to mates. The thick bone acted as a shock absorber, distributing impact forces and preventing brain damage. These herbivorous giants possess small, peg-like teeth suited for cropping vegetation, but relatively poor for chewing. Like Edaphosaurus before them, they likely relied on gut fermentation to break down plant material, requiring massive digestive systems to process the enormous quantities of food needed to fuel their bulk. Their rib cages were correspondingly wide and deep, creating barrel-shaped torsos that dominated their body profiles. They were the mega herbivores of their time, analogous to elephants or rhinos in modern ecosystems. On the carnivorous side, Dinocephalians produced some of the most fearsome predators of the Permian. Ankylosaurus was a monster among monsters. Up to 6 meters long and weighing perhaps 600 kilograms, it was the apex predator of Middle Permian South Africa. Its skull was massive and powerfully built, with enormous temporal openings for jaw muscles that could generate crushing bite forces. The teeth were large, blade-like and recurved, perfect for slicing through the thick hides of herbivorous Dinocephalians. The hunting strategy of Ankylosaurus likely involved ambush predation, followed by a devastating bite. Its limbs, while more upright than earlier synapsids, were still not built for sustained running. But they didn't need to be. In environments where prey animals were themselves slow and bulky, speed mattered less than striking power and bite force. Ankylosaurus could deliver crippling wounds that would either kill immediately or weaken prey enough for follow-up attacks. Bone pathology in herbivore fossils shows healed bite marks matching Ankylosaurus tooth patterns, evidence of violent encounters where prey animals somehow survived. The most peculiar carnivorous Dinocephalians were the Titanosuchians, including Titanosuchus itself. These predators had elongated, almost crocodilian skulls with interlocking teeth designed for gripping rather than slicing. They may have hunted in or near water, using ambush tactics similar to modern crocodilians. Their fossils appear in sediments suggesting river and floodplain environments, supporting this semi-aquatic lifestyle hypothesis. The diversity of predatory strategies among carnivorous Dinocephalians shows how rapidly they were evolving to exploit different niches. One of the most remarkable aspects of Dinocephalian biology was their potential for elevated metabolism. Some species show bone microstructure, suggesting rapid growth rates and possibly higher body temperatures than typical reptiles. The thick bone of herbivorous skulls and the massive muscle attachments of carnivorous skulls both indicate high-energy lifestyles. These weren't sluggish, cold-blooded creatures dragging themselves across the landscape. They were active animals that dominated their ecosystems through size, power, and aggression. But despite their success, Dinocephalians vanished surprisingly quickly. By the end of the Middle Permian, they had completely disappeared from the fossil record. The cause of their extinction remains contentious. Some researchers point to climate change, as global temperatures fluctuated and rainfall patterns shifted. Others suggest competition from more advanced theropsids, the next wave of synapsid evolution, drove them to extinction. Whatever the cause, Their disappearance was total and permanent. The Dinocephalians left no descendants. Their evolutionary lineage ended completely, making them a true dead-end branch on the synapside tree. Yet their brief dominance proved that large body size was achievable for land vertebrates, paving the way for even larger herbivores and predators in later periods. They were evolution's first attempt at creating terrestrial megafauna, and while the experiment ultimately failed, the lessons learned would echo through the rest of vertebrate evolution. Gorgonopsians, the saber-toothed killers. When the Dinocephalians vanished, a new dynasty of predators rose to claim dominion over the late Permian world. These were the Gorgonopsians, named after the Gorgons of Greek mythology, whose gaze could turn victims to stone. The comparison was apt because Gorgonopsians were apex predators so fearsome, so perfectly designed for killing, that they represented the pinnacle of pre-mammalian predator evolution. From roughly 270 to 252 million years ago, they stalked the floodplains and forests of Pangaea, the undisputed masters of their domain, before disappearing forever in the apocalyptic fires of the end Permian extinction. Gorgonopsians were built for one purpose: hunting. Unlike the bulky, sometimes awkward Dinocephalians, Gorgonopsians had sleek, athletic bodies with limbs positioned more directly beneath their torsos. This improved posture allowed for more efficient locomotion and greater endurance, suggesting they could pursue prey over longer distances than earlier predators. Their forelimbs were particularly well developed, likely used to grapple with prey, while their devastating jaws delivered killing bites. The skull of a Gorgonopsian was a masterpiece of predatory engineering. Long and narrow with enormous eye sockets facing forward, it provided excellent depth perception, essential for an active hunter. The temporal openings behind the eyes were massive, accommodating jaw muscles that could generate tremendous bite forces. But the truly distinctive feature was the teeth, particularly the upper canines, which had evolved into genuine saber teeth, elongated, laterally compressed blades designed for precision killing. The largest Gorgonopsian, Inostrensevia, possessed canine teeth up to 12 centimeters long. These weren't blunt crushing teeth or simple pointed gripping teeth. They were evolved cutting implements with serrated edges on both front and back, capable of slicing through skin, muscle, and even bone. The jaw joint was positioned low and far back on the skull, allowing Gorgonopsians to open their mouths incredibly wide, gapes exceeding 90 degrees. This wide gape was necessary to deploy the saber teeth effectively, swinging them downward in slashing bites rather than simple forward bites. Biomechanical studies using CT scans and computer modelling have revealed how Gorgonopsians used these remarkable weapons. Rather than wrestling prey and biting repeatedly like modern big cats, Gorgonopsians likely employed precision strikes to major blood vessels and soft tissues. The saber teeth would puncture and slice simultaneously, causing massive trauma and rapid blood loss. Evidence from fossil bones shows bite marks matching Gorgonopsian tooth spacing on herbivores like Dicynodons and Pareiasaurs, confirming these predator-prey relationships. The diversity within Gorgonopsia was remarkable. Small species like Lycaenops were barely a metre long, about the size of a coyote, and likely hunted smaller prey or juveniles of larger species. Mid-sized forms like Gorgonops itself were roughly leopard-sized, while giants like Inostrensevia reached lengths of 3 to 4 metres and could weigh 300 kilograms or more. This size range allowed Gorgonopsians to dominate multiple predatory niches simultaneously, from small game specialists to apex predators capable of taking down ton-sized herbivores. Sensory capabilities in Gorgonopsians show clear advancement toward mammalian conditions. The large, forward-facing eye sockets suggest excellent vision with binocular overlap, providing depth perception crucial for judging distances when attacking. Skull anatomy indicates enlarged olfactory regions, suggesting a keen sense of smell for tracking prey. Some specimens show pit-like structures on the snout that may have housed whisker-like sensory organs, though this interpretation remains controversial. Regardless, Gorgonopsians were sensory sophisticated in ways their prey often weren't. Fossil trackways attributed to Gorgonopsians show footprints with clawed digits arranged asymmetrically, suggesting digitigrade locomotion, walking on the toes rather than flat-footed. This toe-walking stance, combined with their upright posture, would have improved running efficiency and speed. While they probably couldn't sustain marathon chases, they were likely capable of explosive sprints fast enough to run down most prey over short distances. The geographic range of Gorgonopsians was vast. Fossils have been found in Russia, South Africa, Tanzania, Zambia, and even Antarctica, which during the Permian was positioned closer to the equator and supported lush vegetation. This worldwide distribution indicates Gorgonopsians successfully dispersed across Pangaea, adapting to various environments from seasonal floodplains to more arid uplands. Their success was total. For several million years, no other predator could challenge their dominance. But all dynasties end. When the end Permian extinction struck with volcanic fury, Gorgonopsians were among its first victims. As ecosystems collapsed and prey populations crashed, apex predators had nowhere to turn. Their specialized hunting adaptations, so effective in stable conditions, became liabilities when food chains disintegrated. Not a single Gorgonopsian species survived into the Triassic. The age of saber-toothed proto-mammals ended completely, never to return. Evolution would eventually recreate saber teeth in true mammals millions of years later, but the original design, the Gorgonopsian solution, died with them in the Permian inferno. Dicynodons, the tusked herbivore dynasty. While predators like Gorgonopsians capture our imagination with their ferocity, the true success story of the Permian belongs to a group of herbivores that would outlast every other major synapside lineage of their time. These were the Dicynodons, two dog teeth, named for the pair of prominent tusks that jutted from their upper jaws. Appearing in the Middle Permian and flourishing through the Late Permian, Dicynodons became the most abundant and diverse herbivores on land, filling niches from small burrowers to massive megaherbivores. Remarkably, they would be among the few synapside groups to survive the end Permian extinction, continuing into the Triassic and even reaching the Cretaceous before finally disappearing. The Dicynodont body plan was revolutionary in its simplicity and effectiveness. Their skulls were short and deep with a distinctive parrot-like beak made of keratin covering the front of the jaws. This beak was perfect for cropping vegetation efficiently. No teeth were needed at the front of the mouth. Behind the beak, most Dicynodonts had no teeth at all, except for the characteristic pair of canine tusks. These tusks varied dramatically in size between species and were often larger in males, suggesting they played roles in defense, display, and intraspecific combat. The jaw mechanism of Dicynodonts was unlike anything seen in earlier herbivores. Rather than simply crushing food up and down, Dicynodont jaws could move forward and backward in a propalinal motion, creating a grinding action between the beak and the back of the mouth. This allowed them to process tough plant material far more efficiently than earlier herbivores. Some species developed rough, horny pads on their palates that worked with the lower beak to create grinding surfaces, further enhancing their food processing abilities. Dicynodont diversity was staggering. The smallest species, like Robertia, were about the size of rats, tiny burrowers that may have fed on roots and underground plant parts. Mid-sized forms like Dimetrodon and Cysticephalus were incredibly abundant, with hundreds of specimens found in some fossil localities. These animals dug extensive burrow systems, preserved in the fossil record as helical tunnels descending meters into ancient soil. Evidence suggests they used these burrows for shelter from the harsh Permian climate, possibly even estivating during dry seasons like some modern mammals do. At the opposite extreme were the giants. Lissowichia from the late Triassic reached sizes comparable to modern elephants, up to 9 tons and 5 meters long. But even in the Permian, large Dicynodons like Dinocephalodon and Odontocyclops could weigh several hundred kilograms. These mega-herbivores had massive barrel-shaped bodies, pillar-like legs, and enormous digestive systems capable of fermenting vast quantities of plant material. They were the ecological equivalents of modern rhinos or hippos, dominant herbivores that shape plant communities through their feeding pressure. The tusks of Dicynodons have generated considerable scientific debate. In many species, tusks show continuous growth throughout life and display wear patterns from rubbing against vegetation or soil. They may have been used for digging up roots and tubers, stripping bark, or defending against predators. In species where males had significantly larger tusks than females, display and combat functions seem likely. Fossil evidence shows healed wounds on some skulls, consistent with tusk injuries, supporting the combat hypothesis. One of the most remarkable Dicynodonts was Lystrosaurus, which would become pivotal in understanding the end Permian extinction. This pig-sized herbivore wasn't particularly impressive compared to its larger relatives, but it possessed traits that would prove invaluable for survival. Lystrosaurus was a generalist, capable of eating a wide variety of plant types, digging burrows for protection, and tolerating harsh conditions. When the extinction struck, these generalist traits made all the difference. The success of Dicynodonts can be measured in multiple ways. They achieved incredible species diversity, with over 70 genera identified from the Permian alone. Their geographic distribution spanned all of Pangaea, from South Africa to Russia to Antarctica to South America. Their abundance in fossil assemblages often exceeds 90% of all vertebrate specimens, meaning that in many Permian ecosystems, 90% of all vertebrate specimens, 9 out of 10 animals, were Dicynodonts. This level of dominance is rarely achieved by any herbivore group in Earth's history. Dicynodonts also played crucial ecosystem roles beyond simply eating plants. Their burrowing activities would have aerated soils, mixed nutrients, and created shelters used by other animals. Their droppings fertilized plant communities and dispersed seeds. As prey for Gorgonopsians and other predators, they formed the base of terrestrial food webs, channeling plant energy into the carnivore tier. Permian ecosystems were fundamentally shaped by Dicynodont biology and behavior. When the end Permian extinction arrived, most Dicynodont lineages perished. The specialized giants, the niche-specific burrowers, the narrow dietary specialists, all disappeared. But a handful of generalist species, particularly Lystrosaurus, survived. In the immediate aftermath of the extinction, Lystrosaurus became perhaps the most abundant vertebrate on Earth, accounting for up to 95% of all land vertebrate fossils in early Triassic rocks. This single genus had inherited a devastated planet, and for a brief time they had it almost entirely to themselves. The Dicynodont dynasty would continue for millions more years, a testament to the durability of their fundamental design. Pareiasaurs, the armored megaherbivores. Alongside the Dicynodonts, another group of massive herbivores roamed the late Permian landscape, creatures so heavily armored and bizarrely ornamented that they resembled living fortresses. These were the Pareiasaurs, not synapsids, but rather a separate lineage of reptiles that independently evolved to fill megaherbivore niches. From roughly 266 to 252 million years ago, Pareiasaurs became some of the largest land animals of their time, reaching lengths of 3 meters and weights exceeding a ton. Their combination of size, armor, and bizarre skull ornamentation made them among the most distinctive creatures of the Permian, yet they too would vanish completely in the end Permian extinction. The Pareiasaur body plan was built for defense. Their skeletons were massively constructed, with thick, robust bones that supported tremendous weight. The limbs were pillar-like and positioned vertically beneath the body, true upright posture that allowed efficient support of their bulk. This was necessary because Pareiasaurs were covered in armor. Their skin contained thousands of small, button-like bones called osteoderms embedded in the dermis layer. These osteoderms formed a flexible chainmail that covered most of the body, providing protection from predators while still allowing movement. The skull of a Pareiasaur was where their true strangeness became apparent. Broad and massive, with a blunt snout, the skull was decorated with an array of bony bosses, knobs, and hornlets, projecting from various surfaces. Species like Scutosaurus had elaborate arrangements of these ornaments, giving the head a warty, almost dragon-like appearance. The function of these ornaments remains debated. They may have served display purposes, species recognition, or even limited defensive roles, though their size makes a primarily visual function most likely. Pareiasaur teeth were small and leaf-shaped, arranged in rows that created grinding surfaces suitable for processing plant material. Unlike Dicynodons with their beaks, Pareiasaurs had teeth all around their jaws, suggesting different feeding strategies. Wear patterns indicate they were bulk feeders, consuming large quantities of vegetation without much selectivity. Their jaw mechanics allowed mainly vertical crushing motion, with limited side-to-side grinding. Less sophisticated than Dicynodons, but effective enough for their needs. The best-studied Pareiasaur, Scutosaurus from Russia, reached lengths of around 2.5 meters and weights estimated at 500 to 1,000 kilograms. Its barrel-shaped torso housed an enormous gut for fermenting plant material, while its tail was relatively short and thick. The legs were surprisingly gracile, considering the animal's bulk, suggesting Pareiasaurs weren't as slow and ponderous as once believed. Trackway evidence shows they walked with a fairly efficient gait, and while certainly not fast, they could probably move at moderate speeds when necessary. One fascinating aspect of Pareiasaur biology is their potential relationship to modern turtles. Some paleontologists have proposed that turtles evolved from Pareiasaur-like ancestors, pointing to similarities in skull structure and the presence of dermal armor. However, this hypothesis remains highly controversial, with most recent studies placing turtles elsewhere on the reptile family tree. Still, the independent evolution of armored bodies in both groups demonstrates how effective this defensive strategy can be. Pareiasaurs had a wide geographic distribution, with fossils found in Russia, South Africa, China, Scotland, and Brazil. This indicates they successfully dispersed across much of Pangaea, adapting to different environments from river valleys to upland regions. Different species showed varying degrees of armor development, skull ornamentation, and body proportions, suggesting they were diversifying to fill slightly different ecological roles. In South Africa, multiple Pareiasaur species coexisted with diverse Dicynodons, creating complex herbivore communities. The ecological role of Pareiasaurs was similar to that of modern elephants or rhinos. Large-bodied ecosystem engineers that shaped vegetation through their feeding activities. By consuming and trampling plants, they would have maintained more open habitats and prevented woody plant encroachment. Their dung would have fertilized soils and dispersed seeds. And as massive prey animals, they supported populations of large predators like Gorgonopsians, which likely found the juveniles and weaker adults worth the risk of confronting their formidable armor. Defense in Pareiasaurs was multi-layered. The dermal armor provided baseline protection against bites and claws. Their sheer size made them difficult targets for all but the largest predators. Some evidence suggests they may have used their ornamented skulls in headbutting displays or combat, though whether these displays were directed at predators or rival Pareiasaurs remains unclear. Juveniles, lacking the size advantage of adults, would have been more vulnerable and may have relied on group defense strategies. Despite their evolutionary innovations and success, Pareiasaurs failed to survive the end Permian extinction. Every species disappeared, with the lineage ending completely. Unlike Dicynodons, which had generalist survivors that could weather the catastrophe, Pareiasaurs were all specialists, large-bodied animals requiring stable plant communities and predictable resources. When ecosystems collapsed, they had no fallback strategy. The armor that protected them from predators offered no defense against starvation and environmental chaos. The mega-herbivore niche they occupied would remain empty for millions of years into the Triassic, until new groups of reptiles evolved to fill it. Therocephalians, the transitional predators. Between the fearsome Gorgonopsians and the true mammals that would evolve millions of years later, stood an intermediate group of predators that showcased the progressive mammal-like transformations occurring within the synapsid lineage. These were the Therocephalians, beastheads, a diverse group of carnivorous and omnivorous synapsids that thrived from the Middle Permian through the early Triassic. Ranging in size from cat-sized hunters to bear-sized predators, Therocephalians displayed a fascinating mix of primitive reptilian features and advanced mammalian characteristics, making them crucial to understanding how modern mammals evolved from their synapsid ancestors. Therocephalians first appeared around 270 million years ago, evolving alongside the Gorgonopsians, but following a different evolutionary trajectory. While Gorgonopsians specialized as saber-toothed apex predators, Therocephalians were more diverse in their adaptations. Some were fierce carnivores with powerful jaws and large canine teeth. Others were smaller, more agile hunters that preyed on small vertebrates and large insects. A few late surviving lineages even evolved toward omnivory or insectivory, showing remarkable dietary flexibility. The skull structure of the Therocephalians revealed their transitional nature. Unlike the large temporal openings of Gorgonopsians optimized for massive jaw muscles, Therocephalian skulls had proportionally smaller but more precisely organized muscle attachment sites. This suggested more controlled, sophisticated biting rather than pure power. The teeth showed clear differentiation, incisors for gripping, and large canines for killing, and post-canine teeth for processing food. This heterodonty was more advanced than in Gorgonopsians and represented further steps toward mammalian dental patterns. One of the most remarkable Therocephalian features was evidence of early whiskers. Several well-preserved skulls show tiny pits and grooves on the snout region, where blood vessels and nerves would have supplied sensory structures. In modern mammals, identical patterns indicate whisker follicles. While not conclusive proof, this evidence strongly suggests some Therocephalians had facial whiskers, tactile sensory organs that would have helped them navigate in darkness, detect prey movements, and explore their environment. This would make them the earliest known vertebrates with this distinctly mammalian trait. The late Permian Therocephalian Lycosaurus was a medium-sized predator about the size of a large dog. Its robust skull and powerful jaws suggest it hunted medium-sized prey, possibly including small Dicynodons and Pareiasaurs juveniles. Unlike Gorgonopsians with their specialized saber-tooth killing strategy, Lycosaurus had more generalized dentition suited for various prey types. This generalist approach would prove advantageous during times of environmental stress when specialist predators struggled to find their preferred prey. Another significant Therocephalian was Eucymbersia, which possessed an absolutely unique feature among synapsids: venom delivery. A groove running down the outside of its enlarged canine teeth, combined with a pronounced fossa in the maxilla bone that likely housed a venom gland, strongly suggests this predator could inject toxic saliva into its prey. Modern venomous mammals are extremely rare. Only a few shrews, the platypus, and slow lorises possess this trait. Finding evidence of venom in a Permian synapsid was stunning and demonstrated the diverse predatory strategies being explored during this evolutionary experimental period. Therocephalian diversity expanded in the late Permian, with multiple lineages occupying different niches. Large-bodied forms like Moscarinus competed with Gorgonopsians as apex predators. Medium-sized species hunted smaller prey or scavenged. Small Therocephalians, barely larger than modern rats, pursued insects and small vertebrates in undergrowth and burrows. This adaptive radiation showed Therocephalians were evolutionarily successful, not merely living in the shadows of the dominant Gorgonopsians. Crucially, Therocephalians were among the few synapside predator groups to survive the end Permian extinction. While Gorgonopsians vanished entirely, several Therocephalian lineages made it through, including members of the family Boridae. These survivors were generally smaller, more adaptable species that could subsist on varied diets. In the devastated early Triassic ecosystems, this flexibility was essential. Specialists died, generalists endured. The post-extinction Therocephalians showed even more mammalian characteristics. Some early Triassic forms may have possessed secondary palates, bony shelves separating the nasal passages from the mouth, allowing them to breathe while eating, a key mammalian innovation. Their limbs became more upright, their bodies more streamlined. Evidence from bone microstructure suggests they may have had elevated metabolic rates and possibly even rudimentary fur, though direct fossil evidence of fur is lacking. Despite surviving the greatest extinction in Earth's history, Therocephalians ultimately failed to persist. By the Middle Triassic, they had disappeared, outlasted and outcompeted by the Dicynodons, their close relatives that would eventually give rise to true mammals. The Therocephalians represent a what-if of evolution, a lineage that came tantalizingly close to becoming mammalian, but fell just short, leaving the final transformation to their sister group. They bridged the gap between reptile-like synapsids and true mammals, displaying the gradual accumulation of mammalian traits that would define our lineage. Dicynodons, the almost mammals. The Dicynodons, dog teeth, were the synapsids that came closer to being mammals than any other Permian group, and indeed, they would be the lineage that eventually crossed that threshold into true mammaldom. Appearing in the late Permian around 260 million years ago, Dicynodons exhibited an impressive array of mammalian characteristics, while technically still being synapsid reptiles. They varied from small, shrew-like insectivores to medium-sized omnivores and predators. Their advanced features, complex teeth, sophisticated jaw mechanics, probable fur, and possibly even endothermy, made them the most successful non-mammalian synapsids, surviving the end Permian extinction and thriving throughout the Triassic, before giving rise to the first true mammals in the Jurassic. The Dicynodont skull represented a major leap in jaw evolution. Unlike earlier synapsids, where the jaw was composed of multiple bones with relatively simple articulation, Dicynodonts had reduced the rear jaw bones and expanded the dentary bone, the tooth-bearing bone of the lower jaw. This shift would eventually lead to the mammalian condition, where the lower jaw consists of just the dentary, with the other bones becoming tiny ear ossicles that improve hearing. While Permian Dicynodonts hadn't completed this transition, they were well on the way. The teeth of Dicynodonts were remarkably sophisticated. The incisors were blade-like and positioned for efficient cropping or nipping. The canines were large and prominent, perfect for gripping prey or defending territory. But the real innovation was in the post-canine teeth. These had evolved into complex shapes with multiple cusps and specific wear patterns indicating they could actually chew food. True chewing, with precise occlusion between upper and lower teeth, was a revolutionary advance. It allowed Dicynodonts to extract more nutrients from food by mechanically breaking it down before swallowing, improving digestive efficiency. This chewing ability required another crucial innovation, a secondary palate. Dicynodonts possessed a bony shelf separating the nasal cavity from the mouth, allowing them to breathe while chewing. This might seem trivial, but it was transformative. Earlier synapsids had to choose between breathing and eating. They couldn't do both simultaneously. With a secondary palate, Dicynodonts could process food without suffocating, supporting longer feeding bouts and better energy extraction. This feature also suggests higher metabolic rates, as continuous breathing is necessary for active, warm-blooded lifestyles. Evidence for fur in cynodonts comes from tiny pits on fossilized skull bones, where whisker follicles and associated blood vessels would have been located. If cynodonts had facial whiskers, they almost certainly had body fur as well. The two traits invariably occur together in mammals. Fur provides insulation for maintaining body temperature, strongly suggesting cynodonts were evolving endothermy, the ability to generate and regulate internal body heat. The bone microstructure of cynodonts supports this, showing growth patterns consistent with high metabolic rates. The late Permian cynodont Prochynosuchus was a moderately sized predator about the size of a modern raccoon. It had a sleek, agile build with limbs positioned more directly under the body than earlier synapsids, improving locomotor efficiency. Its teeth indicate a carnivorous diet, likely hunting small vertebrates and large invertebrates. Prochynosuchus fossils have been found in both terrestrial and aquatic deposits, suggesting versatility in habitat use. Another generalist trait that would aid survival during environmental crises. Smaller cynodonts like Thrinaxodon, which survived into the early Triassic, show even more advanced features. This dog-sized predator possessed relatively huge eye sockets, indicating excellent vision, important for an active hunter. Its ribcage suggests the presence of a muscular diaphragm, the sheet of muscle that separates the chest cavity from the abdomen in mammals and assists with breathing. A diaphragm allows more efficient respiration, supporting higher activity levels and metabolic rates. Burrow casts containing Thrinaxodon fossils show these animals created complex underground dens, likely for temperature regulation and protection. The cynodont success story is evident in their survival through the end Permian extinction. Multiple lineages made it through, unlike most other synapside groups. Their versatility, varied body sizes, dietary flexibility, burrowing behavior, and advanced physiology provided multiple strategies for enduring ecosystem collapse. In the early Triassic, cynodonts diversified rapidly, filling niches left vacant by extinct groups. They range from tiny insectivores to mid-sized carnivores and even some herbivorous forms. One early Triassic cynodont lineage, the Pareiasaurs, would eventually give rise to the first true mammals around 225 million years ago in the late Triassic. The transition from cynodont to mammal involved several key changes: the final reduction of jaw bones with some migrating into the middle ear, the evolution of specialized mammalian teeth, molars with precise chewing surfaces, live birth in some groups, and lactation for feeding young. But most of these transitions were gradual refinements of traits cynodonts had already begun developing. The Permian cynodonts didn't become mammals themselves, but they laid the groundwork for that transformation. They demonstrated that mammalian features didn't appear all at once in a single revolutionary leap. They accumulated gradually through evolutionary stages, each providing incremental advantages. The cynodonts were the penultimate chapter in the synapside story, the last major group before the emergence of true mammals. Their success endured far beyond the Permian catastrophe, proving that their evolutionary innovations were robust enough to weather even the worst extinction event in Earth's history. Gorgonopsians, the armored river giants. While synapsids dominated terrestrial environments, other lineages occupied different corners of the Permian world. Among the strangest were the Gorgonopsians, heavily armored amphibians that prowled rivers, lakes, and swamps throughout the late Permian and into the Triassic. These creatures looked like a bizarre mashup of crocodiles and giant salamanders, covered in thick bony plates and built for an aquatic or semi-aquatic lifestyle. Reaching lengths of up to 2 meters, Gorgonopsians were apex predators in freshwater ecosystems, ambushing fish, smaller amphibians, and any unfortunate animal that ventured too close to the water's edge. The name Croniosuchian roughly translates to time crocodile, reflecting both their crocodile-like appearance and their long evolutionary duration. They first appeared in the Permian and persisted into the Triassic, making them remarkably successful by Permian standards. However, they weren't actually closely related to crocodiles. Those would evolve much later. Croniosuchians were members of a different amphibian lineage entirely, one that independently evolved armoured, predatory body plans suited for aquatic environments. The most distinctive feature of Croniosuchians was their armour. The back and flanks were covered in rectangular bony plates called osteoderms, arranged in neat rows that created a flexible but protective shield. These weren't just thick scales, they were genuine bone embedded in the skin, similar to what we see in modern crocodilians and some lizards. The ventral side was less heavily armoured, suggesting Croniosuchians spent much time lying in ambush on river or lake bottoms, where the belly was less exposed to attack. The skull of Croniosuchians was broad, flat and triangular, with eyes positioned on top, the classic setup for an aquatic ambush predator. This arrangement allowed them to lie mostly submerged with only eyes and nostrils above water, watching for prey. The jaws were lined with numerous sharp conical teeth, perfect for gripping slippery fish and other aquatic prey. Unlike the differentiated teeth of synapsids, Croniosuchian teeth were mostly uniform in size and shape, following the typical amphibian pattern. Croniosuchian limbs were relatively short and sturdy, positioned somewhat laterally from the body. While capable of terrestrial movement, fossils and trackways confirm they could come ashore. They were most effective in water. The tail was long, deep and muscular, providing the main propulsion during swimming. Movement would have been eel-like, with lateral undulations of the body and tail driving the animal forward through the water while the limbs were tucked against the body for streamlining. The best-known Croniosuchian, Croniosaurus from Russia, lived during the late Permian in river systems that flowed across the northern parts of Pangaea. Its fossils are found in sediments indicating slow-moving seasonal rivers, environments where ambush predation would be highly effective. During dry seasons, these rivers might have fragmented into isolated pools, concentrating prey and providing ideal hunting opportunities. During wet seasons, Croniosuchians could have followed fish migrations up and down river systems. Another notable genus, Croniosuchus, showed subtle differences in skull shape and armour arrangement, suggesting different species were specialising for slightly different ecological roles or prey types. Some had broader, more robust skulls suited for crushing hard-shelled prey, while others had narrower skulls, better for catching fast-moving fish. This diversification indicates Croniosuchians were evolutionarily active and adaptable, not just relic survivors from earlier times. Evidence suggests Croniosuchians were ectothermic, cold-blooded like modern amphibians and reptiles. Their armour would have helped retain heat absorbed from the environment, allowing them to remain active longer in variable temperatures. However, this also meant they were vulnerable to extreme cold and likely limited to lower and middle latitudes, where water temperatures remained tolerable year-round. During the Permian, global climates were generally warm enough to support them across broad geographic areas. The lifestyle of Croniosuchians likely resembled modern crocodilians in many ways. They would have been patient, opportunistic predators, spending much time motionless, waiting for prey to approach. Quick strikes delivered by powerful jaws and reinforced by body weight would have overwhelmed most victims. Unlike the active, pursuit-hunting Gorgonopsians on land, Croniosuchians represented a different predatory strategy: energy-efficient ambush tactics perfected over millions of years of evolution. Croniosuchians survived the end Permian extinction, making them one of the few predatory lineages to do so. Their aquatic lifestyle may have provided some insulation from the worst terrestrial effects of the extinction. Freshwater ecosystems, while certainly affected, may have offered refugia, where conditions remain tolerable enough for specialized aquatic predators to persist. Early Triassic Croniosuchian fossils show they continued their lifestyle largely unchanged, still armored river hunters in a recovering world. However, their Triassic survival was temporary. By the Middle Triassic, Croniosuchians had disappeared, replaced by new groups of aquatic reptiles better adapted to the changing conditions. True crocodilians would eventually evolve and occupy similar niches with even greater success. Croniosuchians represent another evolutionary experiment, successful for tens of millions of years, but ultimately superseded by later designs. They showed one way to be an armored aquatic predator, a strategy that worked brilliantly for a time before the changing world demanded something different. Mesosaurus, the first aquatic reptiles. While synapsids conquered the land and Croniosuchians prowled freshwater systems, another group attempted a different evolutionary experiment, returning to fully aquatic life. Mesosaurus was an early reptile that took the dramatic step of abandoning terrestrial existence and adapting entirely to life in water. Living during the early Permian, roughly 299 to 280 million years ago, Mesosaurus was one of the first reptiles to become fully aquatic, predating the famous marine reptiles of the Mesozoic by tens of millions of years. Small, elongated, and specialized for swimming, Mesosaurus showed that reptiles could successfully invade aquatic niches, pioneering a lifestyle many groups would later adopt. Mesosaurus was relatively small, typically less than a meter in length, with half of that being tail. The body was slender and streamlined, built for efficient movement through water rather than the bulky power of terrestrial animals. The tail was long, deep, and laterally compressed, a perfect swimming organ that undulated side to side to provide thrust. The limbs were modified into webbed paddles with elongated digits connected by skin membranes. These weren't as extreme as the flippers of later marine reptiles, but they were clear adaptations for aquatic locomotion, used for steering and stability rather than propulsion. The skull of Mesosaurus was long, narrow, and filled with numerous thin, needle-like teeth that projected slightly outward. These weren't the teeth of a fierce predator attacking large prey. They were filtering or grasping structures for catching small aquatic prey. The tooth arrangement suggests Mesosaurus fed primarily on small crustaceans, tiny fish, and other planktonic or near-bottom organisms. Some researchers propose the teeth acted as a sieve, allowing Mesosaurus to strain small prey from water and sediment, making it one of the earliest filter-feeding vertebrates. One of the most fascinating aspects of Mesosaurus is its geographic distribution. Fossils have been found exclusively in South America, Brazil and Uruguay, and Southern Africa, South Africa and Namibia, in deposits that were once parts of freshwater lakes or brackish coastal lagoons. This distribution was critical evidence for the theory of continental drift. When Alfred Wegener proposed that continents had once been joined, skeptics demanded an explanation for how identical freshwater animals could appear on opposite sides of the Atlantic Ocean. Mesosaurus provided that evidence. It simply couldn't have crossed saltwater oceans, meaning the continents must have been connected when Mesosaurus lived. The environments where Mesosaurus lived were unique. These weren't open ocean habitats, but rather restricted basins, inland lakes or lagoons with limited connection to the sea. The water was likely brackish or even fresh, with seasonal variations in salinity and temperature. Sediments show evidence of stratification, with deeper waters being anoxic, lacking oxygen. Mesosaurus probably inhabited the upper oxygenated layers, diving down to feed on the bottom but returning to the surface regularly to breathe. The skeleton of Mesosaurus shows adaptation suggesting it was still tied to air breathing, like all reptiles. The ribs were thick and heavy, a condition called pachyostosis, which added weight and helped the animal remain submerged despite air-filled lungs. Many modern aquatic mammals like manatees have similar heavy bones for ballast. The density of the skeleton suggests Mesosaurus wasn't a fast, open-water swimmer, but rather a slow cruiser that could hover or sink to desired depths with minimal effort. Reproduction in Mesosaurus remains mysterious since we have no direct fossil evidence of eggs, embryos, or live birth. As an early reptile, it probably laid eggs like most reptiles. However, being fully aquatic poses challenges. Did females return to land to lay eggs, like modern sea turtles? Or had they evolved to give live birth in water, as some later marine reptiles did? The lack of nearby terrestrial deposits with Mesosaurus remains suggests they might not have come ashore regularly, but without direct evidence, their reproductive mode remains uncertain. The ecology of Mesosaurus indicates it occupied the small aquatic predator niche, feeding on abundant microorganisms and small animals in its restricted lake systems. These ecosystems were productive, supporting dense populations of Mesosaurus. Some fossil sites contain hundreds of specimens in small areas, suggesting mass mortality events, possibly from lake anoxia, drought, or volcanic activity. These mass death assemblages provide rich data about Mesosaurus anatomy and population structure. Mesosaurus went extinct by the end of the early Permian, disappearing as climate patterns shifted and the specific lake systems it depended on changed or vanished. The species was highly specialized for particular environmental conditions: warm, stratified, semi-enclosed water bodies rich in small prey. When those conditions disappeared, Mesosaurus had no backup strategy. It hadn't diversified into multiple species occupying different niches, making it vulnerable to environmental change. Despite its extinction, Mesosaurus demonstrated that reptiles could successfully transition to aquatic life. This experiment would be repeated many times throughout reptile evolution. Plesiosaurs, ichthyosaurs, mosasaurs, and many other groups would later invade marine environments, often achieving far greater sizes and diversity than Mesosaurus. But Mesosaurus was first, the pioneering species that showed the reptilian body plan could be modified for swimming, diving, and hunting in water. It was an evolutionary trial run, successful for millions of years before ending, but validating an approach that later groups would perfect. Camptohiniids, the egg-laying pioneers. While synapsids dominated discussions of Permian terrestrial life, they weren't the only vertebrates walking the land. The camptohiniids were early reptiles, true reptiles, members of the lineage that would eventually lead to lizards, snakes, crocodiles, birds, and dinosaurs. Small to medium-sized animals superficially resembling robust lizards, camptohiniids were among the earliest amniotes to achieve significant diversity and ecological success. They pioneered the amniotic egg, the shelled egg that could be laid on land, freeing vertebrates from dependence on water for reproduction. This single innovation would prove more revolutionary than almost any other in vertebrate history. Camptohiniids appeared in the late Carboniferous and flourished through the early Permian before declining by the late Permian. They range from tiny, lizard-sized insectivores to larger, more robust herbivores. The diversity within the group showed reptiles were rapidly exploring different ecological niches, not simply living in the shadows of synapsids. In some early Permian ecosystems, camptohiniids were remarkably abundant, occasionally even more common than small synapsids in fossil assemblages. The skull of camptohiniids was solid and compact, with relatively small temporal openings. The anapside condition seen in turtles, but likely ancestral for reptiles generally. Their teeth varied depending on species and diet. Early camptohiniids had simple, pointed teeth, suited for catching insects and small vertebrates. Later forms, particularly the larger herbivorous species, evolved multiple rows of teeth, forming broad grinding surfaces. This dental adaptation allowed them to process tough plant material, making them among the earliest reptilian herbivores. One remarkable captohinid was Captohinus itself, a common early Permian genus found across North America. About the size of a modern iguana, it had a robust build with strong limbs and a moderately long tail. Skull structure and toothwear suggest Captohinus was omnivorous, eating insects, small vertebrates, and plant material opportunistically. Its abundance in fossil sites indicates it was a successful generalist, able to exploit various food sources and habitats. Larger captohinids, like Mesozoic, reached lengths of over a metre and were specialised herbivores. Their jaws contained multiple rows of teeth, sometimes 5 or more parallel rows, creating extensive grinding platforms. These dental batteries were independently evolved solutions to the same problem Dicynodons and later herbivores faced: how to efficiently process fibrous plant material. While the solutions looked different, Dicynodons used beaks and palatal surfaces, captohinids used multiple tooth rows, they achieved similar functional results. The captohinid egg was their most important contribution to vertebrate evolution. Unlike amphibian eggs that must remain moist and are vulnerable to desiccation, the amniotic egg has a leathery or hard shell that protects the embryo while allowing gas exchange. Inside, specialized membranes, the amnion, chorion, and allantois, provide cushioning, oxygen transfer, and waste storage. This closed system meant eggs could be laid on land, in burrows, or in nests far from water, dramatically expanding the range of habitats where reptiles could reproduce. This reproductive freedom meant captohinids and their reptilian relatives could colonize environments amphibians couldn't: arid uplands, seasonal floodplains far from permanent water, and other marginal habitats. The amniotic egg was an emancipation proclamation for vertebrates, unlocking vast terrestrial regions and ultimately enabling the rise of dinosaurs, mammals, and birds. Without this innovation, terrestrial vertebrate evolution would have remained constrained to water-adjacent environments. Evidence for captohinid behaviour comes from trace fossils and bone bed assemblages. Some fossil sites contain multiple individuals of various ages together, suggesting possible social behaviour, or at least aggregation at favourable locations. Burrow structures associated with captohinid remains hint they may have sought shelter underground, either to escape temperature extremes or predators. This behavioural flexibility would have enhanced their survival in the variable Permian climate. Captohinids faced competition and predation from various sources. Small species were prey for carnivorous synapsids, while larger herbivorous captohinids competed with Dicynodons for plant resources. Despite this, they maintained significant populations through the early Permian, proving that reptiles could hold their own against synapside dominance. Their success demonstrated that the amniote split between synapsids and reptiles had created two equally valid approaches to terrestrial life. By the late Permian, captohinid diversity had declined significantly. Only a few lineages persisted, and these disappeared entirely in the end Permian extinction. The reasons for their decline before the extinction are unclear, perhaps changing climates, increasing predation pressure, or competition from more advanced reptile groups. Regardless, captohinids had accomplished their evolutionary mission, establishing reptiles as permanent terrestrial vertebrates and pioneering the reproductive strategy that would define amniote success. Their lineage ended, but their innovations lived on in every reptile and bird that followed. Bolosaurids, the tiny tank herbivores. Among the smallest and strangest Permian reptiles were the bolosaurids, pug-sized herbivores with disproportionately massive skulls, bulbous teeth, and heavily built bodies armoured with osteoderms. These miniature tanks lived during the late Permian, roughly 275 to 252 million years ago, and represented yet another independent evolution of herbivory in a terrestrial vertebrate lineage. At a time when most herbivores were large-bodied synapsids, bolosaurids occupied the small herbivore niche, feeding on low-growing vegetation, seeds, and possibly even hard plant structures like nuts that other herbivores couldn't process. Bolosaurus itself, the best-known genus, was tiny, barely 30 centimeters long, including the tail. But what it lacked in size, it compensated for in robust construction. The skull was short, deep, and remarkably strong, with powerful jaw muscles capable of generating impressive bite forces for its size. This skull design wasn't for predation. It was for crushing tough plant material. The teeth were the most distinctive feature, bulbous, almost spherical structures, unlike the sharp or blade-like teeth of carnivores. These teeth worked like mortars and pestles, crushing seeds, hard fruits, stems, and fibrous plant tissues. The body of Bolosaurus was stocky with short legs and a relatively short tail. The skin contained numerous osteoderms, small bony plates embedded in the dermis layer, similar to those in modern armadillos or crocodiles. These osteoderms were arranged in overlapping rows across the back and sides, providing armour against predators. For a small herbivore living in ecosystems filled with carnivorous synapsids and predatory reptiles, this armour would have been crucial. Even juvenile Gorgonopsians or Therocephalians would have found Bolosaurus a difficult, unpalatable meal. The evolutionary origin of bolosaurids connects them to captorhinids, the egg-laying pioneers discussed earlier. Bolosaurids appear to be a specialised offshoot that is adapted specifically for small-bodied herbivory. This shows how the early reptile radiation was exploring diverse ecological strategies, not just trying to compete directly with synapsids in similar niches, but finding underutilised spaces in the ecosystem where reptilian traits offered advantages. Fossil sites containing bolosaurid remains often show they lived in semi-arid to arid environments with seasonal rainfall. These weren't the lush floodplains where large Dicynodons thrived, but more marginal habitats where vegetation was sparser and more seasonal. Bolosaurids may have specialised in seeds and drought-resistant plant parts that remained available during dry seasons when other food sources disappeared. Their small size meant lower absolute food requirements, allowing them to survive on resources insufficient for larger herbivores. The dental wear patterns on bolosaurid teeth tell fascinating stories about their diet. Unlike the vertical wear seen in animals that primarily crush food straight down, bolosaurid teeth show complex, multi-directional wear, indicating they rotated food items while chewing, breaking them down from multiple angles. This sophisticated food processing suggests bolosaurids were achieving high digestive efficiency despite their small size. They weren't just surviving on tough plant material, they were thriving on it. Another bolosaurid, Belabae, shows slightly different skull proportions and tooth shapes, suggesting niche partitioning within the group. While Bolosaurus had very robust, bulbous teeth for crushing extremely hard materials, Belabae had somewhat more blade-like teeth that might have been better for slicing fibrous materials. This diversity indicates bolosaurids weren't just a single species oddity, but a successful radiation, with multiple species dividing available plant resources. The geographic distribution of bolosaurids was wide, with fossils found in North America, Europe, and Russia. This broad range indicates they were successful at dispersing across Pangaea and adapting to various local conditions. Their fossils appear in both lowland and upland deposits, suggesting they weren't restricted to a single habitat type. This ecological flexibility would have been advantageous for survival in the variable Permian climate. Predator-prey relationships involving bolosaurids are difficult to determine directly, But their armour and small size offer clues. The osteoderms would have deterred small to medium-sized predators. The effort to crack through armour to reach a tiny meal might not be worth it. However, larger predators could have overcome this defence. Some fossil specimens show bite marks or broken osteoderms, evidence that at least occasionally bolosaurids ended up as prey despite their armour. Bolosaurids disappeared in the end Permian extinction, joining the vast majority of Permian terrestrial vertebrates in extinction. Their specialised herbivorous lifestyle, dependent on specific plant communities and seasonal food sources, made them vulnerable when ecosystems collapsed. As plants died and seed production plummeted, small herbivores that depended on those resources would have been among the first to suffer. No bolosaurid fossils appear in Triassic rocks. The lineage ended completely. Another experiment in reptilian herbivory that worked for millions of years before circumstances changed too drastically for adaptation. Wiggletosaurids, the gliding reptiles. While most Permian reptiles stayed firmly grounded or took to water, one extraordinary group experimented with an entirely different mode of locomotion: gliding flight. The Wiggletosaurids were small reptiles that evolved elongated ribs forming wing-like structures, allowing them to glide from tree to tree through Permian forests. Living during the late Permian, roughly 260 to 252 million years ago, these aerial pioneers demonstrated that vertebrate flight wasn't a Mesozoic innovation, but had been attempted successfully millions of years earlier. Though they weren't true flyers, they couldn't generate lift through flapping. They achieved controlled aerial descent, opening up three-dimensional forest canopy spaces to reptilian exploitation. The best-known Wigglotosaurid, Coelurosauravus, was a small lizard-like reptile about 40 centimetres long, including the tail. Its body was lightweight with hollow bones, an adaptation for reducing weight while maintaining skeletal strength. But the truly remarkable feature was its ribs. Enormously elongated rib bones extended outward from the body, covered in skin membranes to form wing-like structures. Unlike the wings of birds or bats, where the forelimb skeleton forms the wing, Wigglotosaurid wings were entirely separate structures. The limbs remained free for climbing and grasping, while the rib wings deployed laterally from the body. This design is remarkably similar to modern gliding lizards, the genus Draco, which have evolved essentially identical gliding mechanisms independently. This convergent evolution demonstrates that rib-supported gliding membranes are an effective solution to the problem of controlled descent. Both ancient Wiggletosaurids and modern Draco can control glide angle and direction by adjusting membrane tension and body position, allowing precise landings on target trees. The skull of Coelurosauravus was lightweight and had distinctive horn-like projections extending backward and upward. These weren't true horns, but rather elongated bones that may have supported additional skin membranes or served display functions. The teeth were small and pointed, suited for an insectivorous diet. Insects were likely the primary food source, abundant in Permian forests and providing high-energy nutrition for an active, gliding lifestyle. Small vertebrates might have supplemented the diet opportunistically. The Permian forests where Wiggletosaurids lived were different from modern forests, but equally three-dimensional. Dominated by seed ferns, early conifers, ginkgos, and cycads, these forests provided complex vertical structure with multiple canopy layers. For a small reptile that could glide, this vertical maze offered tremendous advantages. Rather than climbing down one tree, crossing the ground, where predators lurked, and climbing up another tree, an energy-intensive and dangerous journey, Wiggletosaurids could simply glide from canopy to canopy, covering horizontal distances with minimal energy expenditure. Evidence for the gliding lifestyle comes from multiple sources. The elongated ribs couldn't serve any function other than supporting gliding membranes. They were far too long and delicate for anything else. The lightweight skeleton and relatively large surface area created by the extended ribs indicate aerodynamic adaptation. Additionally, Wigglety-saurid fossils appear exclusively in forest deposits, never in open floodplain or arid environments where gliding would provide no advantage. They were specialists, confined to habitats where their unique adaptation was useful. Wigglety-saurid fossils have been found in Germany, England, and Madagascar, indicating a relatively wide distribution during the late Permian. However, they were never abundant. These are rare fossils, suggesting Wigglety-saurids were never major components of Permian ecosystems. This rarity makes sense. Gliding requires specific forest conditions and occupies a narrow ecological niche. They were successful within that niche, but never diversified beyond it. The biomechanics of Wigglety-saurid gliding have been studied using computer models based on fossil measurements. Results suggest they could achieve glide ratios of approximately 2 to 1 to 3 to 1, meaning for every metre of altitude lost, they could travel 2 to 3 metres horizontally. This isn't as efficient as modern flying squirrels, which achieve 4 to 1 or better, but was certainly sufficient for forest canopy movement. They couldn't gain altitude or truly fly, but they could control descent angle, turn in mid-air, and land with precision. Reproduction in Wigglety-saurids remains entirely unknown. No eggs, nests, or juveniles have been found. As reptiles, they almost certainly laid eggs, but whether these were laid in trees, in ground nests, or hidden in vegetation is pure speculation. Juveniles would have needed to develop gliding membranes as they grew, suggesting a gradual transition from purely terrestrial movement in hatchlings to full gliding capability in adults. The end Permian extinction eliminated Wigglety-saurids entirely. Forest ecosystems were particularly hard hit by the extinction. Plants died, forests burned, and the complex vertical structure collapsed. Without forests, gliding offered no advantage, and specialist gliders had no fallback strategy. The Wigglety-saurid experiment ended completely, leaving no descendants. True powered flight wouldn't evolve for another 50 million years when pterosaurs, birds, and bats independently developed the complex adaptations necessary for flapping flight. Wigglety-saurids showed gliding was possible, but they never got the chance to evolve further. Procolophonids, the surviving success story. Not every Permian reptile lineage ended in extinction. While synapsids, Pareiasaurs, and most other groups vanished in the end Permian catastrophe, one modest group of small reptiles not only survived, but thrived afterward, the Procolophonids. These lizard-like reptiles appeared in the late Permian and continued successfully through the entire Triassic, finally disappearing in the early Jurassic after more than 50 million years of existence. Small, stout-bodied and herbivorous, Procolophonids proved that sometimes the unspectacular generalists outlast the mighty specialists. Their success story offers important lessons about survival during mass extinctions and environmental upheaval. Procolophonids were small animals, typically 15 to 30 centimetres in length, with robust, compact bodies and relatively large heads. The skull was distinctive, broad, triangular, and in later species adorned with backward projecting bony spikes or horns. These spikes likely served defensive or display purposes, making Procolophonids more difficult for predators to swallow and possibly serving in intraspecific social interactions. The overall body plan was conservative, without the extreme specialization seen in many Permian reptiles. Their limbs were short and sturdy, positioned somewhat sprawled from the body in typical early reptile fashion, but functional enough for effective terrestrial movement through low vegetation and dense forest understory environments. The teeth of Procolophonids were specialized for herbivory, but in a different way than other herbivorous reptiles. Rather than multiple tooth rows or complex grinding surfaces, procolophonids had broad, chisel-like teeth, forming a simple but effective cutting edge. These teeth were perfect for cropping vegetation and simple crushing, but couldn't process food as thoroughly as the sophisticated dental systems of some synapsids. Instead, procolophonids likely relied on gut fermentation for most digestion, swallowing plant material after minimal oral processing. The jaw structure was relatively simple, with limited ability for complex chewing motions, yet this simplicity proved adequate for their survival needs. One of the keys to procolophonid success was their generalist ecology. Unlike specialized herbivores that relied on specific plant types or habitat conditions, procolophonids could eat various low-growing plants, ferns, cycad leaves, seed fern fronds, even algae and mosses. This dietary flexibility meant they weren't dependent on any single food source. When plant communities changed, procolophonids could shift to whatever was available, buffering them against environmental fluctuations. Stomach content analysis from exceptionally preserved specimens confirms this varied diet, showing remains of multiple plant types within single individuals. Their small size was another advantage. Small animals require less total food than large ones, meaning they can survive in marginal habitats with lower resource availability. They also reproduce faster and reach maturity sooner, allowing populations to recover quickly from losses. During mass extinctions, when large-bodied specialists were most vulnerable, small generalists like procolophonids had inherent survival advantages. They could eke out existence on minimal resources and rebound quickly when conditions improved. Population genetic studies based on fossil abundance suggest procolophonids maintained large population sizes, another factor contributing to their remarkable resilience against extinction pressures. Procolophonid fossils from the late Permian are relatively rare, suggesting they weren't dominant elements of their ecosystems. They lived alongside the more numerous Dicynodons, Pareiasaurs, and other herbivores, occupying a minor ecological role. But when the end Permian extinction struck, this very mediocrity became an asset. While specialized giants dependent on stable, productive ecosystems died out, the modest procolophonids endured. Their low ecological profile and flexible requirements allowed them to survive the devastation. Fossil evidence shows they persisted in refugia, isolated pockets where environmental conditions remained tolerable, before spreading outward as the world slowly recovered. Early Triassic procolophonids show rapid diversification following the extinction. With competition reduced and ecosystems recovering, they evolved into numerous new species filling various small herbivore niches. Some developed more elaborate cranial ornaments, spikes, horns, and bony frills, suggesting increased intraspecific competition and social complexity. Others developed stronger jaws and more robust teeth for processing tougher plant materials. This post-extinction radiation shows procolophonids weren't just passive survivors. They were actively evolving and adapting to new opportunities. Later, procolophonids, particularly Middle and Late Triassic forms, showed interesting specializations. Some developed extremely broad skulls with powerful bite forces, possibly for crushing hard seeds or tough stems. Others had elongated bodies and reduced limbs, suggesting movement through dense vegetation or even semi-fossorial habits. This late Triassic diversity demonstrates procolophonids were continuing to evolve and explore new ecological strategies long after the Permian extinction. The geographic distribution of procolophonids expanded dramatically in the Triassic. Permian forms were limited mainly to high-latitude regions of Pangaea, but Triassic species appear on every continent, indicating successful global dispersal. This cosmopolitan distribution further contributed to their longevity. Populations isolated on different land masses could evolve independently. And extinction in one region didn't doom the entire group. Procolophonids finally disappeared in the early Jurassic, outlasted by changing ecosystem dynamics as dinosaurs diversified and modern-type ecosystems developed. By this time, they had survived far longer than most Permian lineages, adapting through multiple environmental changes and faunal turnovers. Their eventual extinction wasn't due to catastrophe, but rather gradual displacement by more efficient herbivores, a respectable end for a group that had defied the odds for tens of millions of years. The Procolophonid story teaches an important evolutionary lesson. Spectacular specializations and dominant ecological positions don't guarantee long-term survival. Sometimes the humble generalists, the small and flexible species occupying minor niches, are the ones that persist through catastrophes. Procolophonids weren't the rulers of the Permian world, but they outlived nearly everything that was. Their success lay not in dominance, but in adaptability, not in specialization, but in flexibility. Survival strategies that prove effective time and again in Earth's history.